Well, hi, good morning, and thanks so much for joining me here. It's October 14th, and winter is coming slowly. So, we're going to start off by studying the schematic a bit here, but just for fun, I had this box out yesterday, and I just love this picture on the front of this box. It just kills me. No, this is obviously from the this would be the early 70s, I would guess. Check her out there. Peace. Peace. Hey, what happened to everybody going peace? I remember doing that. Peace, brother. What happened to that? I like that. I like that. Peace and love. What happened to all that? Okay. Now, it's still alive and well in me. So, I think we're going to look at the schematic and consider a few more things about this radio before I attempt another alignment on it. That intermittent squealy thing, which is gone at the moment, maybe it's gone for good. If it reoccurs, then I can pursue it some more. And I have loaded a whole bunch more. I'm going to stop in a second here and show you a video from yesterday when I discovered how bad this speaker actually is. Look at all the repair spots on it now. Yeah, so I'm going to stop. I'll play the little piece from yesterday on the speaker, and then we'll carry on with the schematic. Okay, so I've been working away here trying to patch this speaker, and it has not been going well because even as I'm patching holes here, I'm touching the cone with my tool and poking more holes in it. I'm actually kind of going backwards here to some degree. But then I got a smart idea. I thought, well, just how many more cracks are there in here? And maybe I can't see them. And this is why I turned the camera on, because I did this next. So now they can see cracks all along here, here. Look at this. I mean, this area is not torn, but I guess it's just the way the light is being shadowed by structures underneath. But look at all these other cracks. Oh my gosh, the thing is just cracked everywhere. I was just doing little tidbits with some fingernail polish. I'm not sure that's going to make it with this speaker. There's a crack here. Oh my gosh, it's really bad. I thought you'd like to see that. Okay, so here's the schematic, and what I want to focus on is this unusual volume control arrangement here, which I discovered yesterday. I never imagined it was out here. I always figure it's here in the start of the audio circuits, and 99 and 44ths 100% of the time, yeah, that's where it is. But for some reason in this radio, and this is a late 1930s, I think it's a 1938 radio, 1946. Oh my gosh, why did I think it was the 38? 1946, 47, and they're still doing this? I'm stunned. So this is not the simplest thing. This end of the potentiometer here doesn't go to ground directly. It goes through this small 50 ohm resistor, and then it finds a signal ground here. So what's going on with this? Now, from the antenna point of view, it's pretty easy to figure out. If you slide this all the way up here, then you've applied a chassis ground right to the antenna, and you've got nothing across this coil. You got nothing going into the radio. If you put this down here, you have a fair size resistor of unknown amount, because for some reason they didn't bother telling us. Or did they write it right here? No. Did I miss it somewhere? No. So, but anyway, if you put it down here, now you've got this resistor helping build charge or cause flow through the coil here and on into the radio. The thing to look for here that I'm curious about is what's going on over here. So if we come along over to here, we find out, well, this is the feedback coil, if you like, for the local oscillator operating with the 6SA7 here. This is the cathode there, so all the cathode current, R2 is probably fairly big, 22,000, yeah. All the cathode current is headed down here. So any current in the cathode, any alternating current, sets up an alternating current over here. we've got tuning here, and then that is fed to this grid. So that's how the oscillator appears on grid 1 from here. This trimmer is trimming the resonance of this, setting the oscillator frequency. Okay. Now, when this is in this top position and the radio is silent, at that point the ground is further removed from this line because it has this resistance in there. Unless this is like a 10 ohm resistor or something crazy like that. I'm guessing this is a few thousand anyway. So when you want the radio to play loudly and you've slid this down to here, you now have applied a ground to the bottom of this coil past this small resistor. So, and this is about the local oscillator. So this is having some bearing on the operation of the local oscillator. Unless the fact is, how big is C7? C7 is a big one, 0.1. Unless C7 is so strong in this situation that the signals going through here really can't see past it. Can't see any of this. That's possible too. The reason I'm curious about this is because the volume control is a weird operator. You turn it about 1/3 of the way, nothing much happens, and all of a sudden everything comes to life. It's really a terrible volume control. I'm wondering if it's something to do with this. It's affecting the local oscillator strength. I don't know. They try to set this up so strong signal meets strong local oscillator. I don't know. Something very curious about how all this is done. Curious to me anyway. C6 is probably a very small capacitor. 110 pico. So another thing to look at, and really, at least I understand what's, how this is wired up. Let's go look at this situation now. This is quite confusing too, to me. So here we have your usual IF transformer. There's the trimmers for the two coils. All is fine. This is the one I was adjusting when everything went wonky. We come to the output side of this, and this is where I went wrong. I always look at these things and you think, well, this must be primary and this must be secondary. No, it doesn't have to be that way. If you follow the output from here, it goes through this side first, and from here it's working its way, luckily, right to the grid of the output tube. So this is the output from the plate here. They put it through a transformer, it tuned and adjustable transformer. This produces something here in this side of the transformer, the secondary side. So the top of it is hooked up to a diode. So what is being developed in this is being rectified. The rectified result is applied right across this capacitor. C14, is it a 0.01? No, it's very small, 260 pico. How about R7? Is it really big? 270 K. So I was thinking, so this must be the AVC controlling, the AVC speed capacitor, if you like. I think this is AVC. Goes back. R9. R9 is a big isolator. Yeah, 1 mega ohm. And then it gets to the grid. There it is on the grid. Goes back here. Goes through R8. R8 is another biggie, 2 mega ohm isolation resistor, and the DC gets up here, here, and then onto the signal grid. So we have to assume both of these are remote cutoff tubes, or tubes that will respond to a DC voltage on the grid and change their gain. So there we are. So that's what's going on here. I really got turned around because of the way they turned this around. Primary over here. So now it's all rather simple. So this AVC production here is quite isolated away from everything else. I'm thinking maybe I can get on top of this capacitor here, and I'm on the inside of these big resistors, so the low impedance part of the circuit. I should be able to power a meter here without affecting the radio. That's what I'm thinking. And we can watch the ABC voltage. And I'm planning on doing a sweep through here. I have something else to talk about too, but I'm planning on doing a sweep through the IF and see what it looks like. The other thing I want to talk about is the tuning of this transformer. So if this is all about producing an ABC voltage, and the signal through here is going to be still loaded with RF. So C15 would be the signal ground for the bottom of the coil here. C15 is not terribly big either, 350 picofarads. C11, 0.02. 0.02. 0.02, and the R10 is probably a really big one, yeah, 1 megohm, because it's on the grid here. C11 I will have replaced. Well, and what's this? So this is the 175 B plus coming in to operate the plate. So I guess it's just a way to grab. Like why wouldn't you use this other diode here? I mean, I think this diode in the circuit, yeah, here you can see it's just grounded. They want to use a I don't know, it's kind of odd too, because the current flow in here, yeah, it's coming off of here. It's only wait a minute, how's this detected? How is this detected? What's coming through here is the full-blown output of this tube. Usually these tubes are arranged so the detected signal is sent through the amplifier. You detect it or rectify it and then send it through. Am I just reading this all wrong? So we have the top going to the grid. So this is like acting more like an IF amplifier here, I think. It must be. And then the output down through here. So this would be the 455 and everything all mixed together here. The 455 in audio. Where does it get rectified? Well, I don't know. I don't know how this works. Because the only thing that's getting rectified is just one diode connected, and it's connected to this side of this transformer, and it's just developing an ABC voltage. One easy way to throw away the I don't know about that. Yeah, I don't know how this works. Okay, once again, I'm admitting my lack of knowledge here. Oh well, it does work somehow. So the main thing is, though, I can grab the ABC voltage at the top of C14. C14 is a small mica. Top of R7. R7 is a small, physically small resistor right off this coil. I should be able to find this point fairly easily. And then we can check it. And if that works out, we're golden. I think that's it for studying here. Okay. All voltage emitted tube socket to ground to chassis with meter of 1000 ohms per volt. That's a lousy meter, 1000 ohms per volt on highest readable range. So what they're suggesting is use a lousy meter, but use it on the higher ranges. On the higher ranges, its input impedance will be higher. 1000 ohms per volt meter. That's because, and the reason they're doing this is probably because this is what they think everybody had. All the guys doing the work on these radios had meters of this lousy quality. No use telling them how to use meters. They don't know. Okay. Okay, I don't think I'm going to extract any more out of this. Oh, look at this. Yeah, I will. Wire capacitor. So this is that one I've been looking at over and over. C3, there it is there. So C3 is a loose coupling type capacitor, or a gimmick, right between the antenna and the grid. And you know, why is that there? I don't know. They discovered after building this thing that it needed it, and found out in the laboratory experiments that it needed that capacitor. I don't know. I don't know. Something just on a little aside here. Let's go back to. So when I was working in the power company, I was in the distribution planning and design department, and we produced an awful lot of plans on paper, that drawings on paper that went out to the field crews to install cables, move poles, and do all the work they did every day. There was a constant flow of plans coming out of the office, just like any engineering office, just like the schematic we were just looking at. What I came to realize is that the drawing goes out with a fair bit of instructive information on it, some notes and things like that. You know, do this pole first, do this pole second, little things like that. But what it never contains is all the thinking that went into the design that's drawn on the plan. And this is generally true everywhere. So you have your thinking people, designers, engineers, thinking away. Should we do this? What about A or B? And they make decisions. We'll do B. Then they draw the diagram with B on it. Then they give it to a crew out in the field. They pick it up and they go, well, why did they do this? Why do they want B here? There's no explanation on the drawing. So a good field guy gets on the phone and phones back to the office and talks to the design engineer and says, you want B here, don't you really want A? And then they'll explain, no, because you don't know it, but there's another plan coming 3 weeks from now and we need B for that plan. Oh, I didn't know that. No, you can't know that. You're out in the field. So this is a problem, and we face it all the time with these schematics on old radios. Up comes a schematic, but there's nobody there telling you why they put this part here or there or anywhere. We're just left to guess. Or if I were a more advanced radio design engineer, I could probably say exactly what they were. You know, the reason for that capacitor is exactly this. Maybe someday I'll understand all these parts. But for now, you know, this is what humans are good at. Humans are good at going forward in an environment that has insufficient information and insufficient facts and insufficient everything, but you must go forward, and we're really good in those environments. Yeah, believe it or not. Do you believe that? I believe that. Okay, now I've talked myself right out here. I'm going to stop and set up for the sweep check. Maybe first I gotta take a little break here. I've got to identify the AVC point in the radio. Okay, here's something to relax with. I just was outside on my deck and I grabbed this leaf. It's not going to do it justice here in my shop. So maple leaf, you know, this is the kind of leaf that's on the Canadian flag. In Canada, and I'm sure in other northern countries around the world who might have maple trees, I don't think they're just germane to Canada. Certainly they're in the States, no doubt about that. These guys turn these beautiful colors. This one's, it's just not really doing it, but beautiful red, bright red, like this kind of red out there this year. Beautiful leaves. It's just a fantastic show going on in Ontario this year with brilliant red trees. Beautiful stuff. I thought you'd like to see that, because maybe you're in a country far away from me. You've never seen something like that. Okay, now I'm going to go take a break. Okay, I think I'm almost ready here. So I abandoned the idea of trying to monitor the AVC voltage because I became concerned that hooking up my scope or anything to the AVC circuit anywhere is going to disturb it. too much to make it valid. So what I've done is I've done the old standby, which is I've hooked up my scope to the speaker. You can see the scope lead here. So I'm just, whatever comes out of the speaker goes up on the scope. Now for the signal input to the radio, which is connected here to the antenna wire, is the output from this signal generator, which is a sweep generator. And it's sweeping right now. It's sweeping from, just a little higher here, it's sweeping from, I gotta double check this, 425. So 425 is 30 below 455, and it's sweeping up to 485, and 485 is 30 above 455. So 455 is in the middle of the sweep. I should put it on the middle of that screen. The scope here, sweep, is triggered by this output here, actually, which is actually appearing way up here. So one channel becomes the sweep when you put this into XY mode. Anyway, good. So we should turn on the radio. I'll turn on the radio, it'll start howling right away. Let's see what happens here. If it howls, I'll howl too. She's humming. So we're going to get a chance to hear my speaker repair too, if it worked at all. So I got to think about what we're doing here. We're feeding in the sweep signal, but the sweep signal is so low. Ooh, speaker still sounds crappy. Something's definitely rattling on it. Yeah, good luck on this. Okay, we'll set this in the middle. It doesn't really matter where. Something funny there. We'll get the sweep going. What we should hear out of the speakers, a sound like that. I'll put the sweep speed slow, and we'll start bringing it up here. Just bringing up the level. Not quite what you want to hear. Okay. I haven't got the sweep running. Okay, sweep running. There we are. Boy, does that sound like a heartbeat. So the reason you're hearing a whack thump is literally what my hand is doing. It's sweeping forward, and then it sweeps back very quickly, and there's no blanking like in the old television sets. So the sweep actually goes whack, 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 thump, whack, thump, whack. That's what you're kind of hearing there. Okay, that shouldn't really matter whether you sweep it this way or sweep it that way. The difference in the sound of the two sweeps is the speed at which they're going, because the reset is very, very fast. You can kind of see it on the scope here. So now we're going to speed the scope, speed up the sweep speed here. Beat whatever's left of the speaker out of it. There we go. Now I'm going to give you a little better of a camera view on the scope. So that peak represents the strongest point in the sweep process, where the sweep passes through the resonant point of the IF. What is it doing? What is that? You know, it just never fails. Well, I'm going to tune the radio and just see what kind of difference that might actually affect this. Well, another one showed up there on the screen. Yeah, that's right. Doesn't matter how many of these radios I do, there's always a surprise coming, it seems, anyway. Oh, what was all that? There's lots of surprises coming out of this radio. Okay, so I'm not moving. I'm just standing perfectly still here. And now I'm taking a deep breath. Okay, what in heaven's name? Let's speed it up. So it's running, I think it's 100 milliseconds per sweep. Let me turn the volume up a bit. Poor speaker. So I'm gonna jack up the input on the. I'm gonna turn down the volume here. I'm gonna jack up the input on the signal generator. Try to overcome the noise that we can see here. Not really gonna happen that way, is it? So that's not at all the kind of look I'm looking for. I'm not looking for an S sort of thing. I'm looking for a leap up and down. What the heck can you do with that? So part of the problem here is I cannot tune that second, let's call it the AVC transformer, because I broke the top of it. So for now it's untunable. So the name of the game would be whatever this guy's tuned to, this guy should match. As long as it's not too far off 455. Too far off 455 and the scale here will become ridiculous. So what do I do? So I play around the top of these. Oh my God. Oh boy. There's that. There it is. The thing. Make sure my hand's free here. No. You touch this wire here. Why would that do something? Make a pop. So these clips that go on to the top of the tubes that have a top cap, they're made of steel, and because they're made of steel, you can't solder to them. So this connection right here, although sometimes you find solder all over it, and good attempts to solder it, is mostly a mechanical crimp onto this wire. And maybe over time, so is it here? Is it here? Is it in here? Let's see if we can find out if it's in here first. So try to, this is a little tough. Well, I wouldn't say so. I think it's this clip right on the top of the tube. If I grab this, it might. Now is it? So sometimes the grid cap on the top of these tubes comes loose from the tube itself.
I don't think they would in this case. This is not a yeah, usually these top caps are glued to the glass. You know, it's a glass top. So this is probably the cause of all the trouble that I've been having. Right there. Right there. So yeah, it came off pretty easy. So this is a plated steel. And I think the other video I was yapping on about corrosion and how metals form a corrosive layer, which in some cases self-disruptive, like lead, like some lead corrosion, and steel. Steel, by the way, when steel corrodes, the rust is 7 times the volume of the steel it came from, which is why it all goes up and never stops, because it never produces a coating or a seal on the surface of the metal, on steel. So this has probably got zinc on it. Zinc is what you normally would galvanize the stuff with. Zinc itself is conductive, but I think zinc oxide, which is probably what's forming on here, not so much. So what we're going to do here, I got this turned off, yeah. I'm going to try to freshen this guy up a little bit, and plus improve the, I don't know if I can do this with this much paper. I don't know. Yeah, I got too much paper here. Let's see, do I have another way of doing that? Anyway, try this. Yeah, lots of corrosion in there. Now, if you manage to abrade off all the zinc, or if the zinc has corroded away, then it's just steel. But what will happen when they plated the zinc onto the steel, some of the zinc atoms will have moved into the surface of the steel, and vice versa. Some of the steel will have moved into the layer out here. So just under the pure zinc layer is a layer of combined zinc and steel, some atoms thick. And that layer can be fairly anti-corrosive, if you like. So, you know, all I'm doing is just kind of buffing up the high points here. I'm not really scraping the whole thing, but what does it matter? Because only the high points make contact. There's a theory out there, which I don't really buy into, but it says that if you mate together 2 pieces of metal, and this would be in the case of, say, look how sweaty I am today. What's going on? I'm not working that hard. If you mate together 2 connections, and you can picture this in a power company situation with big cables, big lugs, big lug the size of my hand, and another one put onto it like this, big bolts, maybe 4 bolts going through it to hold it down, and that's the connection, bolted connection. There's a theory that says no matter what you do, there's only 3 points of contact under there. If you think about it for a bit, you can kind of understand why that might be said, 3 points of contact. I personally don't buy it, because I think you clamp down the bolts and that, and it bends the metal and creates more and more contact. And how much contact do you really need, and what is contact anyway? So what you're trying to do is get the 2 electron clouds to mix. So do they actually have to be physically touching? I don't even know what that really means. What's that really mean, physically touching? Nothing physically touches anything. So yeah, you got to use your imagination to think about what's going on levels you cannot see. I mean, that's what our imagination's for, isn't it? Help us understand things we can't really see. Now, this is the top of the tube is probably just fine. So let me just so I can say I did it. just a little bit. Yeah, I really don't want to really stick my fingers on it. Now we want this to clamp a little tighter. It's pretty tough. Let's try it with this one. Let's give it the powerhouse here. If I go too far, I won't be able to get this on the tube. So the reason they use steel is for this exact reason, to get the springiness from steel. Can't do this with copper. Copper has no springiness. Okay, she's on there. Really nice and secure. Let's give it. Let's see if we, so that may have been the cause of the oscillation, a poor contact there. Certainly the cause of instability. Still have this horrible hum. I'm going to center the scope display. So theoretically, all things being correct, this stuff here should be right in the middle. Let's start by checking the sweep. The sweep drifts on this sweep generator drifts. Starting at 420 instead of 425. Okay, that's 425, and we're stopping at 480 instead of 485. 485. Okay, good. Let's see what it looks like now. A little closer to the center. Okay, grab that wire. So maybe it's the wire connection right in the tube here. Right in the come on, it made a pretty good noise there. Why not now? Whole tube. I don't know. Good enough though. Okay. Is this radio ever gonna work reliably? Now what are we gonna do about? Oh, so the display looks just well. It's getting closer to what I really want to see here. For sure, if I was doing this on the ABC, we would just have a dip or a rise. We wouldn't get the S shape. So I'm thinking the resonant point is down here, right there, and that this is a bogus something or other. So what can we do? So we can fool with the trimmer capacitors. Let's see what kind of nonsense we can come up with. This is when everything went haywire last time. Here, let me do it this way. It was this one right here. You crazy radio. You want to get a close look at that on the scope? Doing the same thing, turning the screw now. Hey, where as soon as that's just me bringing my hand up close to it. What's that doing? Turning the screw. hey, maybe this is the way it's supposed to be. This looks like it looks when I have two signals from two signal generators. It gives this funny shape here. Is that because that oscillation is in the IF? Because I'm tuning the radio, which shouldn't really affect this. Cut it down. Tune it the other way. Yeah, it does have some kind of effect, but minor. Well, I got no clue what I'm doing here, but I'm having lots of fun doing it. So we can figure out what frequency this is by me moving the start point over until it comes here. And then I can just read it off the signal generator. So I'm going to do that. I'm going to try to do that. So moving the start point over moves the malarkey. So there we are. So the start point is right where the malarkey is. Malarkey is a well-known electronics term, by the way. And the frequency would be...
What would that frequency be?
Okay. Well, that's kind of a new technique I just got there. That's great. Using the signal generator to check that. So she's okay. Now what mode am I in here? I can't remember now. Am I in the one or the other? We're in one or the other. Good thinking, Jim. Let's put the antenna on it again. Take that off. Antenna. Ooh, that didn't make any difference whatsoever on the radio. So it's picking up signals that are being converted to 455, and they're going through the IF, and they're coming out with a oscillation. So at this point, there is an oscillation in the radio, heterodyning with the one generated by incoming signal. Chances are, right where you hear the low point in the oscillation, that's exactly where the station is. Yeah, there's a guy there. So it's in oscillating mode. So if I go back a little bit with this. Wow. What happened? Let's go here. Bring it on again. There it's on. There it's off. Let me adjust the other screw a little bit. Wow. Wow, 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 wow. It really does sound like a wild oscillation in the IF of this radio. And anytime you peak this guy up enough, boom. So if we tune in a station now, and the speaker sounds like crap, this is really not a good deal. Oh boy, 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 boy. That's the station right there. You make out somebody's voice? something there. Huh. What is going wrong with this radio that it's like this? Well, I'd be right back to I made a mistake when I changed the capacitors, or something else happened too. Yeah. I don't know what else to do at the moment. I should think about this a little bit. And yeah, I got to stop and think, because there's no ideas flowing here. I hit the bottom of my bucket. Well, this might be it for today again. Another day of kind of stomping around in circles here around this radio, but we got to do that in order to finally find out what's really going on. I hope. Okay, have a great day. See you later.